Hello, welcome to my presentation. My name is Taryn Mostel, and this is how Linux control groups, or C groups, enable containerization. In the next 12-ish minutes, I'll explain what C groups are, how they work under the hood, and why they are fundamental to container technologies like Docker and Kubernetes. In modern computing, we often need to run multiple applications on a single server, whether microservices, web apps, databases, or background workers. Running each application in a separate full virtual machine works, but it's resource intensive and inefficient, especially when many apps are lightly used. Containers provide a more lightweight alternative. They let many applications share the same host operating system kernel while remaining isolated from each other. But sharing a kernel and hardware resources safely and efficiently requires a mechanism to isolate not just file system or namespaces, but resource usage itself. That mechanism is C groups. So what exactly are C groups? Control groups, often shortened to C groups, are a feature of the Linux kernel that let you group processes and then limit, prioritize, or monitor their resource usage. That might include CPU time, random access memory, disk input-output network bandwidth, and more. In effect, C groups give fine-grained control over how much of the system's limited resources each group of processes can consume, which helps ensure fairness, avoid resource hogging, and keep a shared system stable. A quick historical note: C groups were originally developed by Google around 2006 because they needed a way to safely run thousands of workloads on shared infrastructure. At that scale, even one runaway process could affect search, Gmail, or YouTube traffic. Eventually, the feature was merged into the mainline Linux kernel and later became one of the key pillars that made modern container technology possible. So, why do C groups matter? Without C groups, a single misbehaving process could consume all the CPU, eat up all of the RAM, or saturate disk input-output or network. This would bring down other workloads or even crash the system. This is especially problematic on shared servers or multi-tenant environments or when running many applications at once. C groups solve this by enforcing resource quotas, limiting how much CPU, memory, input-output, or network a group of processes can use. That leads to predictable performance and avoids noisy neighbor problems and makes it feasible to safely run multiple apps on a single host. Under the hood, C groups organize processes into hierarchical groups. Each group can have various controllers attached, such as CPU controller, memory controller, input-output controller, and more. These controllers enforce limits, quotas, or priorities for the resources they govern. For example, a CPU controller can limit how much CPU time a group gets. A memory controller can cap how much RAM it uses. The Linux kernel exposes C groups via a pseudo file system, typically mounted at sysfs cgroup, which allows administrators or container runtimes to configure C groups by creating directories and writing limit values to special files. To make this clearer, here are a few examples. The CPU controller limits how much processing time a container gets. The memory controller can enforce strict usage caps. If a container exceeds them, the kernel can kill it. The PIDs controller prevents a process from spawning unlimited child processes, which protects against fork bombs. The BLK IO controller controls disk throughput, which is important when multiple services share SSDs or cloud storage. Together, these controllers allow the operating system to act almost like a resource accountant, measuring, controlling, and enforcing limits predictably. There are two major versions of C groups, V1 and V2. In C group V1, each resource controller had its own hierarchy. This could lead to complexity and conflicts when combining controllers. In V2, the design was simplified. There's a single unified hierarchy managing all controllers, which makes resource accounting more consistent and management simpler. For many modern Linux distributions and container runtimes, cgroup v2 is now the default and recommended choice. So how do cgroups fit into containerization? Containers are not the same as virtual machines. They don't run a separate guest operating system with its own kernel. Instead, containers share the host operating system's kernel. So to give each container its own sandboxed environment, Linux uses namespaces to isolate things like process IDs, network interfaces, file system mounts, and user IDs. That isolation ensures containers don't interfere with each other's views of the system. But isolation alone isn't enough. You also need resource control to prevent a container from hogging CPU, memory, or input-output. That's where cgroups come in. By combining namespaces for isolation with cgroups for resource control, container runtimes like Docker and orchestration systems like Kubernetes can provide lightweight, efficient, and safe environments for multiple applications on a single host. So here's a simplified example of how you might manually create a cgroup and limit resources for a process. First, you make a directory under sysfs control cgroup, for example, my group, which is what's shown in this example. Then you write limit values. So for instance, writing 50,000, 100,000 to CPU.max restricts CPU usage to roughly half of a core on a system where the period is 100,000 microseconds. Writing 100M to memory.max caps memory usage at 100 megabytes. Finally, you write the process's PID to cgroup.proc and to assign it into that group. Once done, that process is constrained. It cannot exceed the limits you set. Container tools do exactly this, but programmatically, applying cgroup rules automatically to container workloads. If you've ever run a command like docker run memory equals 256M, CPUs equal 0.5, Docker translates those flags directly into cgroup configuration files. So even though using a tool like Docker feels simple, beneath the surface, many low-level cgroup files are being written automatically by the runtime and enforced by the kernel. Containers built on cgroups offer many benefits. They're lightweight because they don't require a full guest operating system. They're efficient thanks to shared kernel and fast startup, and they provide resource isolation to avoid interference between workloads. This enables many containers to run on a single host. This leads to high density, scalability, and efficient utilization of hardware. However, there are trade-offs because containers share the kernel. They don't provide the same isolation level as full virtual machines, so there can be security concerns. Also, misconfigured resource limits may starve a container or trigger out-of-memory kills, and tuning resource constraints appropriately requires care and understanding of workloads. In real-world deployments, orchestration systems like Kubernetes rely heavily on cgroups to manage resource usage across many containers. When you define a container, you often specify resource requests and limits. So this container needs 156 megabytes, which are basically megabytes of RAM, but no more than 512 megabytes. Under the hood, Kubernetes, via the kubelet and container runtime, uses cgroups to enforce those limits. If a container tries to exceed its CPU quota, the kernel throttles it. If it uses too much memory, the kernel may terminate it with the infamous out-of-memory kill. This ensures fairness, prevents noisy neighbor issue where one container drains all the resources, and improves stability when many workloads run on the same host. In conclusion, cgroups are a fundamental Linux kernel mechanism that allow control over resource usage by grouping processes and enforcing limits on CPU, memory, input-output, and more. When combined with namespaces, which, like I said, just provide isolation, cgroups make that containerization possible, which enables lightweight, efficient, scalable, and isolated application execution. Containers built on cgroups offer many advantages over traditional virtual machines in terms of performance and resource efficiency, but they also require careful configuration, and they share the host kernel, which can raise security or isolation concerns. Ultimately, understanding cgroups is pretty essential if you want to work with container-based architectures such as Docker or Kubernetes, or build scalable, stable, multi-tenant systems. Lastly, these are the references and credits. Thank you for watching, and if you'd like to dive deeper, these are all of the references I used, and I look forward to any questions. Thank you, and goodbye.